informations, and then you may have some categorical predictors in your data, and then logistic regression. I hope I can cover all these topics in this session. Now let's come to the correlation. So correlation essentially is a measure of linear association between two variables, if you say, and if those who have little exposure of statistics, so they can understand there are two kind of correlation you can calculate. One is called, let's say, theoretical correlation, population correlation. One is sample correlation. So generally, when you work with data, we calculate the sample correlation coefficient. So essentially, it is defined by this formula. This is the sample correlation. You can rewrite it in this way. You can, since here x bar represent sample mean, or you can say just average. So you have two columns essentially. One we call x, another we call y, and then we have x1, x2. We have like data like this. You have data like this, y1, y2, yn. Obviously, they have to be equal length, and then you can call this r of xy. So correlation coefficient between this and this vector or these columns. X bar sample mean of column x, y bar sample mean of column y, sx is the standard deviation of column x. So it is defined by, sx is defined by 1 over n minus 1 summation I is equal to 1 to n xi minus x bar whole square. So this is sx.
ये नहीं खराब
Similarly,
कर रहे हैं हम, आप तो
similarly
इसी
you
में
have
सी साइन
your
कर रहे हैं, डेटा नहीं खराब कर रहे हैं, है ना?
so similarly you have your sy, and then you can basically write rxy like this, or alternatively like this. So important thing is that this is a very simple measure of linear association between two variables, and if you understand, let's say, you know that to view your data you can have a scatter plot. You can plot x on x-axis and here on y-axis, and then x1 y1 is this point, x2 y2 maybe this point, x3 y3 like this. So in this case, what is happening? In this case, if x is increasing, then y is also increasing. So this means there is a positive correlation between the variables, and if all the points fall between on a same line, straight line like this, one line, then the correlation is highest, and then correlation become equal to 1 in this case. So this means that why it is important in data analysis. So many times you want to see whether one variable can you give information about the another variable. If one is high, another is high, one is low, another is low, that kind of thing. Or so for example, let's say height and weight. You understand, and height of a person and weight of a person may have a positive correlation, good degree of positive correlation. Person expenditure and income. One person income, one person expenditure is connected to the income. So they have high correlation. Person IQ is connected to the salary and or the income. IQ connected to the income, degree connected to the income. So in this way, you can have a basic analysis like whether these two variables are correlated. However, you should not basically confuse that. Okay, this if two variables has high level of correlation, then they not necessarily to be correlated. It may happen by chance also. Just two variables have high correlation, so they need not to be connected with each other. So for example, in many books, actually very extreme examples are given. Let's say uh, this one, fertilizer sale in fertilizer sales in, let's say, this kind of thing in Congo. If this is one variable x, and y is the Chinese Chinese equity market, another variable. So by some maybe without any connection they may have a high good degree of correlation, but it doesn't mean that okay, fertilizer sale in Congo can predict the Chinese equity market. Why? So this connection has to come from some relationship, some theory or something. So two variable, so just having high correlation doesn't mean that they are connected. The connection comes from some other thing. So that's why we here sometimes that correlation and causation are two different things. Causation is not correlation, that one is causing the other to move or something, right? Now what are the property of sample correlation? So it is, if when r greater than 0, it is said to have sample data pairs are positively correlated. When it is less than 0, they are negatively correlated. It can be proved that the it correlation coefficient always fall between -1 and +1. So if there is a positive relationship between them with positive slope, like as we are saying that all the data points fall in some line, this is a positive slope line, then in this case r is equal to 1. If all the data fall in this line, data point fall with negative slope, then r is equal to -1. And if data look like this, like a circle, like this, if data is like this, then r is equal to 0 here, almost 0, need not to be exactly 0. So there is no, if one is increasing then another, you cannot say surely whether it is increasing or decreasing. So that's why there is almost no correlation between them. So as I told that okay, scatter plot can be one measure where you can assess at least whether there is a positive correlation, negative correlation, high level of correlation. You cannot tell exactly what correlation unless they fall in a line on a line. Then in this case, r is greater than 0, and also you can say that or maybe uh, in this case close to 1. You can say at least, you cannot tell exactly, but close to 1 it may be there since there is a good correlation. In this case, r is less than 0. In this case, you can say r will be close to 0 by looking at these charts. Now let us come to with this with simple linear regression. So essentially what happens that in uh, many real life applications, you want to predict another variable, one variable based on another variable. So you have two variables, one is x, another is y. So you have data like this. So x, we call this variable x here as the independent variable, independent variable, or this is also called the predictor, or this is also called the uh, input variable. There are different names, input variable, and economics people use some exogenous, endogenous kind of word also. So just you have to check. Then similarly, y called here the dependent variable, or predicted variable or the output variable. And also it is sometimes it is also called label also. Label, you can say some number. In machine learning sense they call categorical data like features or label also sometimes. Now what happened, this x and y could be, you can have many example here. X could be your income and y could be your expenditure. This could be one problem. So basically you want to predict expenditure based on income. X could be your IQ score, right? And Y could be the income or salary. X could be the height or healthy population. Y could be the weight. So this means there are so many possibilities that you want to predict one variable based on the another variable. So in simple linear regression, now let us come to simple linear regression. So in simple linear regression, you have one predictor. So in simple linear regression SLR, you have one predictor only. You have one predictor. Now let us come to the simple linear regression is a statistical technique that allows us to study relationship between two continuous or quantity variables. The one variable is denoted by x is called independent input feature explanatory or predictor variable. The another variable y is called here dependent output response or predicted variable. So there are different names. Now, what is the history of regression? So the term regression was coined by Francis Galton. So what Galton observed that if he took the height of parents, father height basically, and then father height, and then let's say if there is a father, there are several people with height, father height is 60 inch written here, and then the children height vary actually. These are children height. So you have taken one parent with 60-inch height. The children height is this only. Another parent, the children height is this, and so it varies. So several children height has been taken here. Then similarly, take the parents of height 65, and then children height vary. Their children heights vary. 70 it varies, 75 it varies. So essentially, it's saying then what is happening that you can see one thing here that 60-inch parent, their average height has crossed 60. So 60 is here. So the average is here. So this has crossed 60, this number. You take a 65 parent, so it has almost also crossed 65 or it is close to 65. Then 70, it is down below 70. You take the average here, it is below 75. So what Galton observed that okay, the the shorter parents, their children height is more, it has increased, and taller parents, their children height on average has decreased. So 75 average is not 75, it is below. So this phenomena he called regression to mediocrity. Like everybody is going toward the mediocrity, medium. Basically, uh, there. So this means that there will not be very taller parents will not be there. Taller children will not be there in future generation since their height has increased. So everybody is going towards the similar height. Shorter parents children height is more, taller parents children height is less. That's why however on average taller parents has taller children, smaller parents has still smaller children, that he has concluded. So there is this connection in averages, and so this phenomena he called regression. Now what is the modern so regression essentially in statistics is used from maybe hundreds of years in, but today in machine learning sense regression has a different meaning, little bit different. So what it's saying that you take several input variables x1 x2 xp, and then you have a variable y. So based on x1 x2 xp you predict y. So whatever way you predict, if this is a numerical quantity, numerical variable or quantity variable, this is a numerical thing, then this is called regression. And if it is a categorical thing, then this is called classification. So if y is numerical, this is called regression. And if y is categorical, this is called classification. Now, whatever way you do, so this means essentially our idea is that y hat is equal to, we try to find out a function f which connects x1, x2, xp, and so this is your problem. So you find a function f which basically can help you in telling your y. based on the input x1, x2, xp. And whatever way you do this, this is called a regression problem in general. So does expenditure depends on income? Does crop yield depends on fertilizers, rainfall, sunshine, soil type, etc., and so on. So all these problems comes under the regression. Now, so just you have to remember that regression is a statistical relationship, not a deterministic relationship. So in deterministic relationship, you have a perfect relationship. You give the input, you get the perfect output. In statistical relationship, you cannot predict whatever way the perfect output, the exact output. It has to have some errors. So that's why this is called a statistical relationship rather than a deterministic relationship. So for example, if you want to predict even the let's say expenditure based on income, based on income, so even you will find a variation. A person with 50,000 income may have 10,000 expenditure. Another person 50,000 income may have 20,000 expenditure. Another person may have 8,000 expenditure. So essentially, with the same person, you can have different numbers. So that's why you never predict the exact value. You only try to predict the average value here. So maybe the average expenditure of a person, different person with salary 50,000, maybe let's say 15,000 or whatever. So you never try to predict the exact value. You try to predict only the average value. So that's why this is a statistical relationship. Now let us come to, so in deterministic relationship you have perfect relationship. Statistical you can tell with some error that okay, for this the average value turns out to be this. Now so before going to regression, let us try to understand the difference between regression and interpolation. So interpolation, you may have heard that okay, what is interpolation? That you have x here, you have y, some points are given to you, then you try to find a curve which pass through all these points. That is the interpolation problem. Interpolation. In regression, whatever happen is that you have more points actually. You don't have two, 3 points, or and even you can have for a one, you can have several same values actually here. Like here, there is no vertical value. That two value are not like this. In regression, it is never the case. Since a function cannot take two values, like for single argument, single input. But in regression, that's why you try to predict a line which better approximate the data. It need not to pass through all the points. So if you understand this little mathematically, so consider a set of n data points xi, yi, 1 to I to n. Suppose it is known that these points lie on a function, this function form y is equal to fxm. It could be anything, polynomial, sine kind of function, or trigonometric function, whatever, where represents a function family and represents a set of parameters. So this is basically a quadratic function. Now, in each case, we assume that the function family form, but we do not know the function parameters. So you know that okay, you have to fit a parameter. You have to fit, let's say in this case, fx is equal to ax square plus bx plus c. So in interpolation, you try to find out a, b, c, which are unknown to you, and then once you have this, then you have the interpolation. So, so for example, in this case, you have different functions which are passing through the points, and so this is interpolation problem, right? So in parametric regression, we want to find a parameter set m such that fxim approximate yi, and in interpolation, you find that exactly yi. So that's what we are saying, that if you have let's say this data interpolation problem will be like this, that it pass through this curve, this interpolation problem. Regression problem will be that need not to pass through but better approximate the data, that is inter regression. So that is the difference between the two, so you should not confuse. Now let us comes to linear models first. So you can have uh, different kind of regression. So we focus on the let's say linear models. So a model is said to be linear when it is linear in parameters. So remember this, linear in parameter. So in such a case, del y by del beta j should not depends on beta j. So for example, this model qualify as a linear model. The reason is that this is linear in parameter. So del, if you take del y by del beta 0, this is the partial derivative. So this is just beta 1 x. So it is independent of beta 0. If you take del y by del, sorry, it is not this, it is, sorry, I have written this 1, it is 1 del y by del beta 1, that is just x. So this and this are independent of the parameters. So this basically this qualify as a linear model. So this qualify as a linear model. Next comes is, let's say this one y equal to beta 0 x to the power beta 1. So if you take here del y by del beta 0, then that is x to the power beta 1. So this depend on beta 1. So that's why this doesn't qualify as a linear model. So remember that a linear model or linear regression is which, where if you take the partial derivative with respect to the parameters, then it is independent of the parameters. There is no parameter. So here still parameter is there. That's why this is not a linear model. This model is a linear model. It is called polynomial regression. It is a quadratic polynomial, but still this qualify. This is little counterintuitive, but this qualify as a linear model. So this is equal to 1 del y by del beta 1 some is equal to x del y by del beta 2 is equal to x square. So this qualify as a linear model since its partial derivative are independent of the parameters. So this is very simple definition, but this is not a linear function. You can see that this is not a linear. This is a polynomial thing, but still this is a linear regression model. Now just this part, if you want to skip this, we can skip conditional. So only thing is that what we are saying that you want to predict the average, this kind of thing. So expected value of y, this is the average of y given x, that you know x. So you want to predict y given x. So important thing is that how do you estimate beta 0 and beta 1? So once you have the model, so how do you estimate? So so what we do, that let's say we have these data points, again I'm writing some points here, and let's say this is our best fit line. So you calculate the error. So this is the error. So this height, since this is the best fitting line, so you are predicting at this point value to be this. So this will be the predicted value, this circle predicted value, and this star that we are putting here, this will be the actual value. This is the actual value, actual value. And so whatever this height is your error for this data point, particular data point. So similarly, you calculate error for all the data points. So this is also error. This is also error, and this is the exactly on same line. So this is also whatever comes is the error. So now one thing is that you take, so this is one line, another line could be this, so you have to choose the best line out of these. So how do you do this? So you calculate the error, calculate the total error, and choose beta 0 and beta 1 in such a way that minimize the error, that minimize your total error. That's how you estimate your beta 0 and beta 1. Okay. Now there is a issue in this. So when you add the error, so essentially let's say these are your error, or you have n data points, and your error is nothing but summation epsilon I is equal to 1 to n. So in this case, what is going to be there, that okay, if I put a line this, so if I have this line, then some error will be positive, some will be negative, so they will cancel out each other, but that is not good. The reason is that you you don't want to cancel out. Let's say there is a error of plus 5 and there is a error of minus 5, so essentially if you do the total it becomes 0, but this is not that is not the total error, since plus 5 minus 5 you cannot cancel out. That's why you can consider mode here, that you take, you remove the sign and then you consider this, but that is also not very practical. The reason is that the mode function is very difficult to deal, like you cannot take the derivative and other thing of the argument here, and that's why the better way to consider is that you take epsilon I squared. So this is called, if you take the, this is called residual sum of square, RSS, or so this is nothing but summation I is equal to 1 to n total error, and we call this epsilon I square. So what is epsilon I square? So this is nothing but summation I is equal to 1 to n, the actual value yi, this is your actual value, and then the predicted value will be beta 0 minus beta 1 xi. You can put hat if you want, since these are just the estimate and the square of this. So this, if you put plus sign here, we can, I put the bracket, I can close. So this is the predicted value in our predicted value, and this is the actual value. And so you take this error, and once you define this function, then you minimize the error to get beta 0 hat and beta 1 hat. So now how you do it? So let me just, so let us call this function s, and which is a function of two variable beta 0 and beta 1, and then you write in this way, summation I is equal to 1 to n yi minus beta 0 minus beta 1 xi whole square. And you already know, you know yi and xi, but you don't know beta 0 and beta 1, which are the best, which best represent your data. Then what you do, you know that in calculus, that if you have to maximize, you have to find the point where the function is taking maximum value or minimum value. So the simple approach is that you calculate the critical point by taking the derivative, and then you put that equal to 0, and then you calculate the second derivative and you check whether it is basically positive negative. So if it is negative, this is the maximum, or if it is positive, this is the minimum. So you calculate del s by del beta 0. So just what you have to do, you write here, so this become 2 summation I is equal to 1 to n yi minus beta 0 minus beta 1 xi into minus 1. You put that equal to 0. So this whole line, whole equation become, this becomes summation I is equal to 1 to n yi minus beta 0 minus beta 1 xi. So if you open the summation everywhere, so this becomes summation yi minus n beta 0 minus beta 1 summation xi, that is equal to 0. And then so this just implies if you divide by everything by n, so this become y bar, this become minus beta 0 minus beta 1 x bar, that is equal to 0. And so y bar is equal to beta 0 plus beta 1 x bar. So this means whatever line you want to find, that pass through the averages of both the columns. So if let's say you have this data, and let's say this is the average here, average of all the x, all the y, then the regression line whatever is will pass through this point. And similarly, when you take the derivative with respect to del s by del beta 1 is equal to 0, you put this. So this implies this equation. So I am not going to do all the calculation, but this is very easy to do. You just take the partial derivative with respect to beta 1, and then automatically you will you can solve this. So hope this is clear. Only thing is that you have to just take the derivative with respect to beta 1 and then you put it equal to 0. So we are calling this beta 1 hat, since this may not be exactly the true value, that uh, this is just the estimate that we are getting from the data. The reason is that if that's why we are calling this estimate. The reason is that if I have 100 points in my data, then you have beta 0 and beta 1 different. If you take 1000 points in your data, more data points, then beta 0 beta 1 value will change. So that's why we don't call them exact value. We depend on the number of data points in your data, and the sample that you have taken. If you basically different sample also, that's why these are called just estimate. Beta 0 and beta 0 beta 1 are we are calling in this way, are the true value of the parameter, true value that you don't know. But based on the data that you have, you get beta 0 hat and beta 1 hat, and these are called the estimate. You can get the true value if you have very large data set. If you have 100 points, you have different estimate. You have 1000 points, you have different estimate. You have 5000 points, you have different estimate. But you can show that for large data, beta 0, you reach close to the true value if you have large data set, and this is called law of large number. So your beta 0 and beta 0 and beta 1 hat will be close to beta 0 beta with large data. Now one more thing, that when you fit a regression, so from machine learning point of view, this is fine, that okay, once you fit the regression, then you calculate the errors. So this is called, so once you have the model, you have y true value, you calculate the estimated value y hat. So y is your true value, y hat is estimated value. So you can calculate mean squared error, MSE. There is a measure of mean squared error. That is nothing but if you have n data points, 1 by n, I is equal to 1 to n yi minus yi hat square. So this is called mean squared error. So let's say you have 10 algorithms. You have, let's say, linear regression, you have multiple linear regression, you have, let's say, decision tree, you have support vector machine. Then to know whether your model is basically which model is doing good on your data, you can compare their mean squared errors, like which one is giving the lowest error. You can consider that model in your prediction. Or generally what you do, you don't take the the error, you take the test error, data on the test error, and then you can compare. But however, when you in statistics, the several techniques has been developed, and these are called linear regression diagnostic. Since whatever model you are fitting, linear regression you are fitting, that depend on several assumptions. So if those assumptions are not satisfied, then your model actually maybe, let's say, not very reliable, and that's why you have to see the assumptions of the model also. That is important. So the linear regression is sensitive to outliers. That is one thing, and hence we assume that there are no outliers in the data. What is the meaning of this? So just you can understand by an example. Let's say you have this data set. So if you estimate a linear regression model, that will be like something like this, some line. Now suppose I have this data set only, but with a small variation. Just I'll add that variation. So I have, let's say, one outlier. Outlier is that data point which basically has a value larger than, or comparatively which we have very differently from other data points. So this is a rough definition I can say. So let's say I have this data point also. I have these data points and this data point. Now to compensate, if this data point also put in the data, then to compensate to minimize the error, the line will become something like this, maybe like this. So this is the line without outlier in the left side, and the right side is the line with outlier. So in this way, it has totally changed the line, and then there will be large prediction errors also. Yes, for example, this data value is this. In this case, this data value is predicted here, but in this case, for whatever data point here, this value is predicted to be this on the line. This data, this value. So there is a large error here due to this. So that's why this outlier totally affect the linear regression model, and that's why linear regression is very sensitive to outliers. The relationship between dependent and independent variable is approximately linear. So it work if the linear relationship. Let's say if there is no linear relationship, then there will be problem obviously. For example, if you have data like this, let's say you have data like this, maybe like this. So then there will be you better fit a polynomial regression on this rather than linear regression. So linear regression will be giving value like this. The error has mean zero. The error term has constant variance. So constant variance, this data constant variance is basically, this is called homoscedasticity. So your data should be homoscedastic, and the errors are normally distributed. So if so, so generally what we do, we fit the regression first, and then after fitting the regression, you check whether the assumptions are satisfied or not by the error. So what we do, so to check whether there is a outliers in the data, so you can do the box and whisker plot of the, let's say, yi. So you consider the y data, dependent variable, and for this data you get the box and whisker plot. Box and whisker plot. And so box and whisker plot, you can see that this kind of plot, essentially you have here, you give the data, then median is called median also, median is basically the data point such that 50% of the data point are lower than this and 50% of data points are higher than this. So median is also called the second quartile, or this is also called the 50th percentile. So you may have heard the word percentile. The percentile essentially means that if you have 50th percentile, so this means 50% of the students have performed better than you, and 50% of the students have performed worse than you. This is called lower quartile, this is called Q1, this is called median Q2, and this is called Q3. So Q1 means that 25% of the data point fall below this and 75% fall above this. So you can have a box and whisker flow. So you can basically detect the outlier using IQR. This is a technique, very basic technique, that okay, which, how do you say quantitatively that which data points are outlier, I mean, which are not outlier. So in this way, it say that if you calculate Q1 minus 1.5 IQR and this interval Q3 plus 1.5 IQR, and then the data within this interval are called normal data, and the outside this interval are called outliers. So for example, let's say if you have this data, then how do you identify the outliers? So the first thing is that okay, you put the data in ascending order, you identify Q1, Q2, Q1 and Q3 out of this. So Q1, so there are total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 data points. So the simple idea that you divide by 11 by 4. So that numbers turns out to be 2 point, I think 75. Okay. So this means, so this is a fractional number. So the integer above this is 3. Above this, the first integer is 3. So the third data point is your Q1. So third data point is basically, this is first, this is second. So this is your Q1. Similarly, if you have to identify Q3, then you remove the last two, and then from the end, if you remove the last two, so here we remove the first two, here we remove the last two. So this is your Q3. And then IQR is called interquartile range, that is Q3 minus Q1, that turns out to be 5. And then based on this logic, you calculate the interval Q1 minus this. So the data points which are within this interval are called normal, and outside this is called outlier. So outside this interval fall is, okay, this data point you can consider 11. Okay, it is 37, this is 11. So 11 is your outlier. So that's how you do it. Scatter plot basically help you, obviously, as I told that okay, to assess uh, this thing. So now we have assumed that in our model that your errors are normally distributed. So we have assumed that errors are normally distributed. So as I told you that you calculate for all the data points epsilon I, and that is denoted by yi minus yi hat. So these are our errors. And now we want to, let's say we have n data points, so we get for all the data points n errors. So this is a vector, and now we want to check whether this vector is normal or not. So you have to know how to check whether your whatever data is given to you, whether that is normal or not. So what you have to do, so the, you know that okay, one thing you can do, you can do the histogram plot. So if you know little bit programming language, maybe Python or R or even Excel, you can do this. So you can do the histogram plot. So histogram plots are like this, these plots. And once you do the upload, so essentially it look like this, then this is called normally distributed. So that's why what you have to check. You can do the histogram plot, or another way is that you can do the quantile plot. These plots are available in Python or R. So essentially what you do, you put the normal theoretical quantiles on the x-axis and the normal data quantiles on the y-axis, and once then you put them, and if they fall on a straight line like y is equal to x line, then this means that the normal quantiles and theoretical quantiles are same, since when y is equal to x, so this means x is one value, another is y another value. So this means if they are same, they fall on a line, and so their quantiles match, and that's why they are called as the coming from the same distribution, so they are normal. Another way of those who have maybe some exposure to statistics, you can go to the test. There are different tests to check whether your data is normal or not. These are called statistical tests. So you have Kolmogorov-Smirnov test, you have Anderson-Darling test, Jack-Barra test, Shapiro-Wilk test. All these tests basically can be used, or some of them can be used, all of them can be used to assess whether your data is normal distributed or not. So once you know that your data is normally distributed, then you satisfy that okay, whatever assumption you assume in your regression model, that is satisfying. That's why you can trust more on your model. Okay, and then how do you check whether homoscedasticity? So in this data, you see that okay, if you put a line and you put another line maybe here, so you can put a parallel line, and so that all data points fall between these two parallel lines. If I put a line here and then I try to put a parallel line, maybe something here, then some data points fall outside this. So this means that what is happening, that here the width is increasing, and then it is keep decreasing like this, or you put like this, and then so on. So here there is a more width of data. So this means you can put boundary like this, triangular. So this is a problem, heteroscedasticity. Your variance is increasing. So in this case, uh, basically what happens that your uh, method, like your regression, whatever you have done, whatever, actually main problem comes with the estimates, or their basically hypothesis test, that comes to the main problem. So then you have to be careful in this case, is that your data is heteroscedastic. Now how do you check it? So we do the error plots, we do the residual plots. So you put x, on x-axis the date independent variable, and on y-axis you put the residuals or the errors. So these are errors, basically errors. And then you will find that okay, in the uh, if your model is good, then you have this kind of thing. If you have heteroscedasticity, then you don't have this, so you have boundary like this. So this is homoscedasticity. So this is called homoscedasticity, and this is heteroscedasticity. And in this case, there is a problem of basically there is a curve kind of thing. So this means that you have to change your model to non-linear model. That will be better. Okay, so I have covered basically the simple linear regression case. So in remember that in simple linear regression case, you have one predictor or one independent variable, right? Now let me just let me just show you actually how it can be done in Excel. Just very simple. Python basically also can be done in simple way. I'll show you if I have some time. Otherwise, it is not very difficult. So let's say I generate the synthetic data. Hope you can see my this screen also. I have this data and then I drag it to some, let's say, 20 data points, and let's say this is insert, this is my x independent variable, and this is my dependent variable, which is nothing but 3 plus 5 into x, this, and then I just change some number to be, I change this number to be 65, this number to be 80. So I have some data, just I have generated some synthetic data, and this 41 and 27. So I have generated this data, maybe 40. Let's see. So this is synthetic data. Now what you can do, just this is very simple to do in Excel. You go to data, you go to data analysis. There is a tools here, and then you can see everything here. You can find the correlation between them. So you will find obviously the high correlation between them, as you can expect from this. So correlation, you put the input range. So let's say we put the two columns here, and then we get the correlation. So these are the correlation. So the correlation come like this. So the correlation is 0.997826. So very high correlation between them. So this means they are linearly, almost linearly dependent of each other. So linearly dependent basically means one can be put as a linear combination of other, and then you can also do the find the regression. So correlation, and then you go down. Here is your regression. You select. So it asks you input y range. Input y range is my this data, and input x range is my this data. And then just you have to put OK, and automatically you get a big table here. Automatically you can get the similar table in Python also, but Excel, just I need not to write any code, I can write directly this. So you can see few things here. It says that we have 20 data points in our data, observations 20, it is showing 20 data points. Then you see here, so this is saying that okay, your my model is intercept and x variable. So it's saying that my model is y is equal to 3.28. Let me write this roughly, 3.28 plus 4.92 into x. This is the model. This is the model that you obtain by using the data. So this means essentially you can predict your y based on this model. If you somebody supply you x, you can tell the corresponding y based on this information. And then the another thing that people in computer science domain don't study much is they basically focus only on error. This error, mean squared, this one, which one they follow, this multiple r, it is a standard error, this error, control B. So if you have 10 algorithms, then basically in you can compare this error with all the algorithm standard error, and then the one can choose the algorithm which gives the minimum error, this much. But in statistics there are different way to look at this whether model is good or not. So one is this app statistic. So here this significance app, this is close to 0, so it says that the model is significant. Another way to check whether the intercept term or the variable x is helping in prediction. So you can see the p-value column this here also, this column, control B. So these value are if these value are close to 0 or less than 0.05, if these values are less than 0.05, then you say that okay, your variable basically are helpful in predicting y. So they are help, basically the model is good. So this value is 0.002, so way lower than 0.05. This value is almost 0. It's saying the 10 to the power minus 22, so very low. So this means your model is doing good. So that's why how you have to assess your model based on these are called goodness of fit measure for regression, like p value, t value, the app statistic, the r square, adjusted r square. So you can see here r square also. This. So if your r square is close to 1, so that is very good. Now let us move further. So what we have discussed is just one predictor. So we have discussed in simple linear regression, you have y is equal to beta 0 plus beta 1 x. So you have one predictor. In multiple linear regression, however, you can have more than one predictor. You have beta 0 plus beta 1 x1 plus in general model beta 2 x2 plus beta p xp. And obviously we add here error term to know to say that okay, you don't predict perfectly. There will be some error which will have positive negative value. So you are trying to predict the average. So you know that, let's say if somebody, as we discussed the example of salary. So salary of a person. Let's say this is the salary of a person. Salary. Then salary of a person may depend on x1. It could be just the IQ level. X2 could be, let's say, maybe degree, whatever he has obtained, or you can remove some variable also. This could be the marks, percentage of marks, CGPA, whatever. So that's why in real life situation, one variable may depend on several other variables, or it can be held, it can be predicted based on some other variable. So this is called multiple linear regression problem, and this is a linear model. So we have y is equal to beta 0 plus beta 1 x1 plus beta p x3 plus epsilon. And then you can have y1 is equal to beta 0 plus beta 1 x11. So we can write data like this. Essentially what we are saying that you have data in very basically maybe we have written it here in this way. So this is called, this is your y, where y here now a vector. This total thing can be called as capital X, which is basically, so this is your x1 column, this is your x2 column, and this is your xp column. You have a predictor. These are the coefficients beta, and these are the epsilon. So this model can be called as y is equal to x beta plus epsilon. But remember that y, x, beta, and epsilon, these are not now scalars, but these are either matrix or vectors. So this is a n cross 1 vector. This is a n cross m, sorry, p plus 1. This is a p plus 1 into 1. This, and this is n cross 1. So this total become n cross 1. This total become n cross 1. So this is n cross 1. So mathematically this is consistent as a matrix operations, right? Now how do you do here parameter estimation? So parameter estimation can be done based on, so we use here little bit matrix operation. So essentially Let us write in matrix form little bit. So we write S beta. S beta is equal to I is equal to 1 to an epsilon I square, which can be written as epsilon transpose epsilon. So you know that epsilon is nothing but here epsilon 1 epsilon n. This way epsilon transpose will be nothing but this row vector epsilon 1 to epsilon n. And if you do epsilon transpose into epsilon, so this will be nothing but epsilon transpose epsilon will be nothing but epsilon 1 square plus epsilon 2 square plus epsilon n square, which we have discussed. This is also called residual sum of squares. And so this can be written as y minus x beta transpose into y minus x beta. If you open it, so this give you the following terms. If you just little bit do manipulation, since these two terms beta transpose x transpose y and y transpose x beta, they have same dimensions, you can merge them together, so this become the term. Now there is a result which basically deal with the in term of basically derivative as a vector derivative kind of thing. So you have m, if you have a mb is b transpose ab, then if you take the derivative with respect to b del mb by del b, then this becomes just 2ab. And you can prove this very in simple way, that you can write a, so basically here what is the meaning of del m b by del b? So this is a vector actually. This is nothing but del m by the component wise derivative del b1 del m by del b2 and so on del m by del bn, whatever this way. So we apply this formula, this logic here on this part. So that's why we call del s beta by del beta is nothing but y transpose y is independent of beta, so this becomes 0. So beta transpose x transpose beta. So x transpose x play like a role of a here in this case. You match this to this. So a is equal to here x transpose x and b is here beta. So based on this information, this become 2a beta, 2ab. So this becomes this part, and here for this part, this becomes just minus 2x transpose y. You take the second derivative, then this becomes just 2x transpose x, and then you this is always a positive quantity. You know that x transpose x is always greater than equal to 0. So this is a non-negative quantity, and that's why even if this in matrix form, if this is a let's say scalar, then you can write this. Otherwise, you have to write non-negative definite, and then beta hat become. So if you just put this equal to 0, so to get the beta, you have to put this equal to 0, and so this become 2x transpose x beta minus 2x transpose y is equal to 0. So this become beta is equal to x transpose x inverse x transpose y. So this way you can calculate the beta directly by using the data. Since x and y will be given to you, the reason is that this algorithm comes under a supervised learning algorithm. Any doubt till here? Like how do you calculate beta head by using the data? Okay, so you can calculate this. Now in Python this is very easy to calculate. You just have to just pass it And so what we can do, just I'll show you how to do this in Excel also, since this is important to understand like what we are doing. So let's say I take this data, but I'll also add some other data. So now my model Y also depend on two variables, that is here uh, I call here this 3, 4, 5, in this way. So I have two variables now. So I am generating just synthetic variable data. We can take real world data also. But anyway, that doesn't change much. Only thing you have to understand the method. And so let's say we have this data. So directly you can use your data analysis tool pack again, and then you can, now you have to see your input variable. So input variable become here this much. Then you have to go with your input variable this, and then you can see that in this case now you have, okay, there is some issue since we have taken these two variables are basically linearly dependent, and that's why there is some issues coming. So we have to change little bit the data. So what I have to do is I take it uh, maybe, okay, I change it to some numbers. Let's say 3. Okay, is equal to 3 plus equal to 1 plus. Yes, I'm generating data, so don't worry about much. That's what I'm doing. This is nothing actually much here. The 2 plus 11. Oh, anyway, so okay. Sorry, so just it is taking. I can write something here. 2, 3, 3, 4, 3, 4, 5, 6, 7, 8, 9. Okay, just some data I have generated, so don't worry about this much. So just what I want to show is that okay, how you basically can do it. So one thing is that okay, as I told you that okay, you go here data analysis again, and then you select your regression, you select your Y range, and then you select your A2 to B21. So this is correct. So you have this seed. So now the first thing you can check is that okay, Now you have x variable 1. These are your input variable or independent variable, two variable, x variable 1, and then you can see the p value. As I told you that this is important. So it's saying that this first intercept is fine. This is also 0, since 10 to the power minus 12, and this is 0.48. So this is not less than 0.05. So this is not very helpful. The variable 2 is not very helpful in predicting the your y. Second thing that is, what you can do is you can do it by the formula. As we have discussed, the estimate beta I am writing here. So your beta is nothing but x transpose x, and this whole inverse x transpose y. This is nothing but your x transpose x inverse, and then you have its inverse minus 1, and then you have x transpose. This is your formula or your coefficients. So you can do it manually also. So what you can do, this data is your x. Whatever I have selected, this is your x. So this is your x. So you can take the transpose of this, and there is a way here that you can put, okay, copy. Let me copy it again. This part only. So this is your x, and then you put paste special, and then obviously there is a values here, and then you can put transpose. So this is your x. Let me put it like this. Okay, so just to make it visible to you both the things. So this is your x transpose. Sorry, x transpose. Now let us come here. This is your x transpose, and now we want to calculate. Let's say this number, as we discussed already, we should know x transpose x. So there is a way here in that you what will be the dimension of x transpose x. So one more thing that you have to remember, that you have to, as I go to my slide. So x is, if you want to get the intercept term, then you have to include a column 111. That will give you the intercept actually. So that's why you have to do the little modification here, that you have to add insert for this particular purpose. You have to add a column with value 111 here, that I have to add. And then same thing that you have to do here, one in transpose also, one, 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 and so on. So this you need actually, and your x transpose x will be a 3 cross 3 matrix. So what you have to do is you have to basically make little space for this. So what I select a 3 cross 3 grid like this. So this I have to calculate x transpose x. So there is a standard way here. You do it here, and then you write matrix multiplication MMULT, and you get the x transpose vector. And so this is your x transpose that I am selecting, and then you have to select your x, which is this, all these three columns till here, and then you close it, and then you put control shift enter. So this is your x transpose x. This vector is your x transpose x for this calculation. Then obviously you have to get the x transpose x inverse also. So I'm writing in that way, x transpose x, and then let me write its inverse also, its inverse. So again you have to select this 3 by 3 matrix, you put equal, and then you write m inverse, matrix inverse, and then you select this in matrix discrete, you do, and then this is your matrix inverse, inverse. Then obviously you have to get x transpose y also. So you have to get x transpose y. So what is the dimension of x transpose y? So x transpose has a dimension of 3 rows into 20 columns. So it will be, and then y has a dimension of 20 rows, 1 column. So this will be a dimension of 3 rows and 1 column. So you have to select like this, 3 rows, 1 column, and then you put again MMULT. I'm just saying that okay, once you understand the steps, then obviously you can do in Python. You need not to work like this, but only thing that okay, you have to understand, right? Like how the things are working, and then what the meaning of this formula, and then you select your Y. This is your Y here, and then obviously you put Control Shift Enter. So this is your X transpose Y, and then your beta become by this formula. Again, you have to select this, and then you pass X this matrix in. Okay, sorry. You have to write first MMULT, and then you pass this matrix, and then obviously you pass this column, and then you put. So these are your coefficients. So these coefficients also we got here. If you see this sheet, so 3 point. These are the coefficient actually. This column. If I put here color, so you see that intercept term is 3.477, 4.73, 3.477, 4.73, and the last one is 0.17026. So remember that in Python also, this is the implementation only. So whenever you supply the data x and y, so what it does, it calculates x transpose x inverse x transpose y to get your coefficients. And once you have your coefficient, then obviously you can then calculate the predicted value and other value. So you can write the code yourself. Only thing that you should know in Python how you basically do the matrix multiplication, matrix inverse, matrix transpose. These three operations you do by using NumPy array, and then you can write your code for matrix multiplication. So I have shown you multiple linear regression how to do in Excel. Obviously Python is not difficult, it is just one line command. Now let us come to polynomial regression. So what is polynomial regression? So polynomial regression essentially is in the again a it is also a linear model. So whenever you will read this, you will find everything under the linear models in the sklearn library. I'll show you. So simple linear regression, multiple linear regression, polynomial all falls under the linear models. So what happens? Let's say you have some sort of data like this. So you have position level, you have salary, and then if you try to fit a linear, basically line here, then if it a line, then it it is not appropriate. The reason is that okay, some value will be deviating too much from the line. So what you can do, you can fit a polynomial between these values, and then you can have a better estimate. So this kind of model y is equal to beta 0 plus beta 1x plus this is called a polynomial regression, and you have to tell that okay what degree you want. So then you can do it. Now then polynomial regression is just like a simple linear regression. So you can multiple linear regression, sorry. So we can estimate the coefficient in polynomial regression using OLS technique, which we have discussed already. So just what you have to do, you have to take, since your model is y is equal to beta 0 plus beta 1, you can call this you can call just x1. The square of that column is you can call as x2, as we discussed. This can call be as just another column x3, and this can be called as another column x4. So similar to the multiple linear regression, this model become y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4. And once you have all these values, this can be just easily estimated by using the earlier technique. So there is nothing much here. So just only thing is that okay, this is just a multiple linear regression. Polynomial regression is nothing but multiple linear regression where this just it work like this. Okay. Now basically little bit about the transformations. So transformations independent or dependent variable removes a number of model problems. So sometimes what happens that as we have said that there could be various problem like non-normality in the data and basically let's say other problem, maybe scale problem. So you can do you have to see the transformation also. So data transformation is a trial and error approach. So obviously there is no sure short. You have to just explore the data. You have to see which transformation may work. For simple linear regression, one can easily see if we required transformation by looking at the scatter plot of x and y. However, in multiple linear regression model, one can't visualize it in a single plot, and hence residual plots are used to check the appropriateness of the model. So just there is a thumbs rule. So log transformation become very important. So so the log transformation is important and helps in many cases. Transforming the predictor or appropriate is it when non-linearity is the only problem. So let's say in this model where you have x-axis, you can see the different scale. The scale is changing very fast. 2000, 4000, 6000. The numbers are changing. So if you take the log of x-axis and then you fit a model between log of the x-axis and then the y remains same, then you have a linear regression, better linear regression model. So sometimes this transformation are helpful. So you may need to transform the data little bit. So for example, y is equal to beta 0 plus beta, as I discussed already, beta 1x is a linear model. Y is equal to beta 0 plus beta 1 log of x is also a linear model by our definition. So this means if you are changing the time to log of time, so you are taking t here, and in this case you are taking log of t. Still, it remain a linear model only. Only thing is that you have transformed these values to log, and then you can have a better prediction, better basically fit. So transforming the response variable value. So this is like transforming the independent variable. You can also transform the dependent variable when non-normality is the problem. So you transform the independent variable when non-linearity is the problem. You transform the dependent variable when normality is the problem. So that's why you have to learn little bit about transformation also if you want to use you want to get good expertise in the regression models. So now another important aspect is that in your model the inputs or basically output, these are numbers, not let's say like here some categories or some binary variables. So consider this example. So in this case, you want to predict the birth weight of a baby, newborn baby, based on the gestation weeks and then the mother's smoking habit. There are two factors like how gestation weeks and the smoking habit. So you can understand yourself that okay, uh, it is very intuitive that if your gestation weeks increase, then the baby weight increase. But what is the connection with the smoking? Whether smoking positively affect the baby weight or negatively affect the baby weight? So in this case, this column is added, right? So to to basically use this categorical predictors, you have to replace this yes and no by number. So there are two ways to do this. One is that okay, you keep the column smoke like this. So one approach is that you keep the column smoke like this only, and you replace yes by 1 and no by 0, so that these become numbers. So this is approach 1. Another approach, you add two columns. Let's say I call this SY, smoke yes, and another I call smoke no. These two columns you have to add, and you can write this 10 for that mother, which is a smoker, and then for that mother, which is, for example, this first value will be replaced by 10. The second value here, like no is coming, so that will be replaced by 01. The third value is yes, so this will be replaced by yes. uh, the fourth value is no, it will be 01. Then you have two yeses, 10 10, and so on. So you have two columns now. So one, so this is one approach that you replace by 10 in single column. And if you have either this approach, so the second approach is preferable when you have several categorical variable. For example, you can have several variables. Here just binary, yes and no, but there could be several. In that case, we prefer this much, this one, like 10 and so on. And then once you have these numbers, then this exactly work like the multiple linear regression. Exactly work like multiple linear regression. You have to just pass these numbers and automatically it will be there. So you can see here, if you even you plot these two, this plot is done in Seaborn library. You can try this Seaborn library. I have done this plot Seaborn. So you see that we have color coded the smokers and non-smokers mothers. We have color. We have put different colors. So smoke yes. You see that these are at lower side on the weight. The these blue dots are lower than the yellow dots. So this means that this smoking actually are negatively affecting the baby weight. So a smoker mother baby will have lower weight. This, since you can fit two lines, one is one, so one line may be like this and another line may be like this. So this line better represent the smoker mothers, and then the upper line represent the non-smoker mother. Both are parallel line. Obviously, we put the both are parallel line, but they may have different intercept. So they are just differing by the intercept. This term intercept, the intercept will be different. So it has on average lower weight than this. Intercept are different. Okay, so far I have covered simple linear regression, multiple, and the polynomial, and the problem of like transformation, how you can transform the data, and then the predictor variable, this categorical variable, if you have categorical variable in your predictors, and then now let us come to logistic regression. So logistic regression, however, is used for classification, not for regression. It is used for classification. Okay. So classification, so binary classification problem work like this. So you have data, maybe let's say in this way. If you have binary classification, so you have your X here, and then you have your Y. So then Y basically is a class. So Y belongs to just two values, either 0 or 1, and X may belongs to the real number. X belongs to R. So y can only take two values. So it may work like this. So some values are maybe just falling x, these are y values here, and some values are like this. So if in this case you fit a linear regression, so that work like this, in this way. But what we want is some kind of function like this, which basically look like something like this, and that is a logistic function. So let us understand the logic. So the logit function takes p values in the range 0 to 1 and transform them to y values in the interval minus infinity to infinity, and is defined by logit p is equal to log of p by 1 minus p. So essentially this function you can understand that if you supply a basically 0 here, so let's say this function logit of 0 will become log of 0. So log of 0 basically is, you can say, minus infinity here, and logit of infinity become log of infinity by 1 minus infinity basically. So logit of infinity become here. Oh, okay, we have to take the value between 0 to 1. Sorry, I have to take 1 here. No, this 0 is fine, but 1 only. So this become 1 by 1 minus 0. So log of infinity that becomes, so that become infinity. So that's why this end is going asymptotically going to infinity, this end going to again infinity at 1, and it become exactly 0 when you have p is equal to half. So if you put p is equal to half, so half by half that become 1, so log 1 is 0, so that value is 0. So but we don't want this function, we want the reverse of this, since our problem is something where data will be of this shape. So you have data point like this here, and then you have data point maybe on x-axis. So that's why we want to use the reverse function of it, and that is called the logistic function, or this is called inverse logic or logistic function. So inverse logic function, the inverse logic or logistic function does the reverse and takes the x values along the real line and transform them to y values in the interval 0 to 1, and is defined by logistic x is equal to e to the power x by 1 plus x for logistic function. So here if you put value between minus infinity to infinity, it will transform the value between 0 and 1. So that is nice, that we want, since we want something like this only. And that's why based on this function, logistic function, we call this problem as logistic regression. So in this way, what you do essentially, so here you can understand that logistic of minus infinity is equal to 0, and logistic of infinity is equal to 1. And so by getting the motivation from this example, so what we do, we define the logistic regression in such a way that you have logistic regression rather than predicting 1 and 0, we predict the probability of the response variable. So you have log of, you define basically px by using the logistic function in this way. So let's say the probability of the point x, or it is taking value 1 or 0, is calculated based on this. So once you have the probability, let's say the probability of you supply x some vector here, or maybe just single variable here, it turns out to 0.9. So this means that the, what is the meaning of this, that the this new value x is essentially taking value 1, its response variable will be 1, has probability 0.9. So essentially then you can, this is probability, but you can convert it into a hard decision. So if this value is more than 0.5, you predict it to be 1. If it is less than 0.5, you predict it to be 0. So that's why you can do the hard basically classification, right? So this is logistic regression. And the main problem is that from the given data, how do you estimate this beta 0 and beta 1? So the estimation problem is done based on the basically likelihood function. So however, it will take some time to tell what is likelihood function, what is the maximum likelihood estimation. So but you can understand that just briefly, that beta 0 and beta 1 you have to estimate from the data. So xi your numerical value, yi are 0 and 1 only. So first you write the likelihood function of the data, that become p xi to the power yi, y minus p xi to the power 1 minus yi. And then generally you can work with likelihood, or when sometime analytically if you want to solve, so low likelihood become important. So you get the log likelihood and then you maximize this. So what we do, choose beta 0 and beta 1 in such a way, beta 1 in such a way that this likelihood is maximized. Is maximized. So that's how you have to do it. And then once you have beta 0 and beta 1, so it use actually iterative methods since it cannot be done analytically. Arrow Newton method or stochastic gradient method basically to estimate beta 0 and beta 1. So here actually I have completed the at least the theoretical part. So if you have questions you can ask me meanwhile, or meanwhile I'm just showing you how it can be done basically in Python. These parts can be done in Python, so I'll go to that part. Essentially, I have installed Anaconda in my PC. So Anaconda comes with Spider as a basically editor. Python, you can use Python in Spider, or you can use Jupyter Notebook, and it is available free of course. Obviously, Anaconda is also, but there are commercial license also, but it is available free also, free version also. So just give me. Okay, so I'll open now Spider on this. Okay, so I'll just show you directly multiple linear regression. I have some data which is available on GitHub also, and other repository also, data repository. This is called 50 startups. This is a known data. So only thing is that just this is already written code. So I'll just explain you what we have done. So you can see that if I just run it, multiple linear regression. So just see that I'll show you variable explorer. So my data set is this. So this is the data. So these are the some 50 startups where the data is available for 50 startups. So here they are saying that okay, there is a column R&D spending, there is a administration spending, there is a column of market spending, and there is a state column like whether this is in which state, and the profit. So what we are saying that the profit depends on the spending on different kind of R&D, administration, marketing, as well as on the state in where the company is there. So you can see these three columns are numerical values, and then the fourth column is a categorical column. Okay, so now the thing is that in the categorical variable, essentially this categorical variable you have to convert into basically the numerical variable. numerical variable. So, and this profit you have to predict. So based on these four things, R&D, administration, marketing, and state, you have to predict the profit by using the multiple linear regression. So this is your data. And then there are standard way of doing this in Python. So this problem is divided into, let's say if you start reading, maybe I'm not sure whether you have used Python already. So this is a library which work with the arrays, NumPy. This is a library matplotlib which work with the plotting. There is a pandas library which work with the data frame. So in this library can read your data directly from your computer, whatever it have different support of different format like CSV, Excel, and RTF. I think different and other. Then from the data I select my independent variables. So this way I select my independent variable, right? And then this way I select my dependent variable. So independent variable except the last column. That's why I put -1 here. You select the independent variable. This way you select your dependent variable. Now the important part is that in your independent variable X, you have one categorical column, and so there is a Python provided framework that is called label encoder and one hot encoder. So it automatically transform your data into it automatically transform your data into basically uh, these columns. As I told you that it will add three columns corresponding to that particular categorical column. So after doing this, you can see that your data will be X here. So you see here. So your data will be like this now. As I told you that it has added three columns corresponding to your this category, those categorical. So it automatically do by one hot encoder. So this you have to go through. Obviously, it will take some time for you to understand. And then what we do generally do, we don't work with on all data. We divide the data into training and testing. So this is also in statistics known as in sample and out of sample analysis. So where you build your model on the training data and you basically check the performance of your data on the testing data. This is called out of sample performance. And so just only thing that you have to do is this much only. Once this is done, this is called data processing part. But for the model, just you have to call from sklearn or linear model. So as I told you that uh, your linear regression or multiple linear regression, everything comes under the basically linear models. So linear regression you call, and then regressor you call this function, and then regressor dot fit. You pass the X training, whichever you want to, and Y training, these two data, and then that's all. Your parameter will be estimated, and then you test, and what you do, then you calculate the predicted value. Y predict, you can pass X test, you can get the predicted values. Okay, so essentially what is happening here, so you can see the coefficients actually for this, and I'll suggest that okay, you calculate these coefficients also based on basically essentially your uh, you calculate these coefficients by using Excel also you can do this. There is nothing here, and you can check your coefficients regression dot coefficient. This is you can check what is the value of these coefficients. So these are the coefficients. So you will get now 3 plus 3, 6 coefficients actually. So these are your 6 coefficients. The for first column this, second column this, third column this, fourth column this, fifth column this, sixth column this. And then you have intercept also the same time. This is not just you have these coefficients, you have the intercept also. So you can check the intercept also. Or if we sorry, the intercept also you can check. And then the predicted value obviously you can check here predicted. These are your y predict value, and you can calculate your error. So you can, this is the y predicted based on the test data. So you can have the y underscore predict based on your training data. So I call this biopredictive training. So this is nothing but regression, which we are calling this regression dot predict, and then you can pass here x underscore train. So if you want to predict corresponding to training data, so this is your y predicted train, and your training error become y underscore train minus y underscore predict underscore train. Yes. So these are your error, and then you can see by plt dot histogram of this train error you can pass, and then you can see the histogram here. So this is a histogram of your error that is coming here. I think this should come. So it is not coming here, but it can come here also. So this is your histogram of error. This error. So you can see that okay, there are some error which are basically very big in negative also. So you can see the histogram of these things. So you can do many things. Once you understand, so what I'll suggest you, if you are just as a beginner in this area, so what you do, you take a data, you essentially compute everything x transpose x inverse x transpose y in Excel. You compute everything in similar way by using the matrix operations in Python. You do the direct computation by using Python, and then that will give you the confidence. Okay, how the things are moving, and you try to understand all the variables here, the training data, testing data, what is the meaning of those, then all the errors and error plots. And once you do all these steps, then automatically you will know all the important component of the regression. And just to show you the polynomial regression, so the same data that I have shown you there, the what is the main difference? The code remains same. The important thing is that all the things are inbuilt in Python sklearn library. All the things are inbuilt. Only if you understand, you have to write this just very few lines. So you have this important library. You read the data from your computer, this data. Then you select the independent variable and dependent variable. You separate them. So this ILO command essentially take the index. This first column represent you that you select all the rows, and this second column represent how many second this entry represent which index column you want to put in your independent variable, and then your dependent variable, and then just from sklearn or linear model import linear regression, since polynomial regression is also a linear regression. And then just what you have to do, this processing of polynomial features, you have to add the polynomial features into the linear regression model. And then what it's saying that okay, you take polynomial regression polynomial features and you added 4-degree polynomial, you make it a 4-degree polynomial, and x polynomial become polynomial dot regression dot transform x. You out of one column you make four columns actually. So if you see this x poly, you will find that what is x poly here. X poly is nothing but here these columns, and obviously one column for the intersect. This column is separate. So these are just four columns here, and this is nothing but x. This is the second column is this is x square, this is x cube, and this is x to the power 4. So automatically to make it into 4, you can do same thing in Excel also, and then once and then you fit the simple regression here. Linear regression you have to fit again. So it is just a linear regression. You have to just first transform the data. You need not to work, you need not to use these functions. You can directly do. You know that if I have a vector x is equal to np dot array, whatever array, you have to just you can do by yourself. 1 2 3. I'm going fast, but hope you understand this. And then what you can do, x into x. I think it should work. So it is just the square of this. In this way, you can automatically convert basically a matrix, and then you can make a data frame out of this, and then you can supply in the polynomial regression model. So essentially, I'll stop here since, and then similarly, logistic regression also you can implement. So I'll take the questions if you have questions. After. So questions, please.
So, what is the main difference between the binary classifier and the logistic regression?
So basically, you can say that logistic regression is a, you can say, particular case of binary classifier. Since binary classifier, you can do it many ways. You can use logistic regression. You can use linear discriminant analysis. You can use quadratic discriminant analysis. You can use decision trees. You can use support vector machine. So you can say, if you say binary classifier has several algorithms. So logistic regression is one of them. You can say you can have naive Bayes. All these things are comes under the binary classifier.
Thank you, sir.
Yes, madam. Thank you.
Thank you, sir. Sir, thank you, sir, for a nice presentation. So, thanks a lot for giving your valuable time for delivering expert lecture in this FDP. Thank you once again, sir.
Thank you, madam. So I hope there is no question, or should I
No,
leave?
sir. There is
I
no
can.
question, sir.
So I can leave, right?
Yes, sir. You can leave now.
Okay,
Okay, thank
madam.
you.
Okay.
Thank you once again, sir.
Thank you, madam. Thank you very much.